Hi everyone, this is Khushi Agarwal and I will be presenting on the topic Signal Processing in Autonomous Vehicles. This will be the agenda for our presentation. Overview. These are the major signal processing techniques used in autonomous vehicles. First, convolution. It is used in object detection to extract features from sensor data. It is also important for image processing tasks like edge detection, motion tracking, and obstacle identification. Next, Fourier transform. It helps in frequency analysis of signals from radar and sonar. It is used to detect Doppler shifts for velocity measurement of moving objects. Third, Kalman filtering. It is a recursive algorithm that refines the sensor data by reducing noise and estimating the vehicle's position and velocity with higher accuracy. Lastly, sensor fusion, which combines the data from multiple sensors to provide a coherent view of the environment. In this presentation, we will majorly be focusing on the applications of convolution and Fourier transform to signal processing in autonomous vehicles. These are the basic components of an autonomous vehicle. The LiDAR unit, which constantly spins and uses laser beams to generate a 360-degree image of the car's surroundings. Radar sensors, which measure the distance from the car to the obstacles. Cameras, which help detect traffic lights and signs, and also help recognize moving objects like pedestrians and bicyclists. The main computer is located in the trunk. It analyzes data from the sensors and compares its stored maps to assess current conditions. How does a self-driving car see? The images depicted on this slide essentially help us understand how a self-driving car detects objects and lanes. Now we will discuss the applications of convolution in signal processing. Convolution is a fundamental operation in CNNs which play a vital role in object detection tasks such as identifying lanes and obstacles in autonomous vehicles. Convolution is used to match signals by correlating transmitted and received radar signals. This is essential for distance measurement. The transmitted radar signal is convolved with the reflected signal, yielding the correlation that helps determine the object's distance and velocity. The mathematical expression for the convolution of two signals is shown on the slide. Now, Gaussian filtering. Why to apply noise filtering in the first place? Before detecting important features like edges and objects, we need to reduce noise in the image. This is where Gaussian filtering comes into play. It smoothens the image and makes it easier to identify the real intensity changes rather than the noise. The mathematical expression for a Gaussian distribution function is shown on the slide. How does Gaussian filtering work? A Gaussian filter slides or convolves over the entire image. Each pixel in the image is assigned a weighted sum of its surrounding pixels. The weights come from the Gaussian function with the center pixel having the most influence. This is shown in the images below. This is an example of Gaussian filtering. First, I take an original green signal and then add some random noise to it to produce a noisy signal. Then I finally show the smooth signal after applying the Gaussian filter. The role of sigma. The role of sigma is to control the spread of the Gaussian filter. This means that a smaller value of sigma will lead to less blurring or smoothing, while a larger value of sigma will lead to more smoothing. This is also illustrated in the graphs shown below, where I have used two different values of sigma for the graphs. Now, another application of convolution is edge detection. Sobel filters are one of the most popular methods used for edge detection using convolution. These are small matrices designed to detect changes in intensity or brightness in an image, which usually indicates edges. These changes represent the boundaries between objects, example road edges or lane markings. These are the horizontal and vertical edge detection matrices respectively. This is an example showing how Sobel filter actually works. A Sobel filter is slid over the entire image, and for each pixel, The filter computes a value by combining the surrounding pixel intensities. This value represents how sharp the change is at that point in the image, thus detecting the edge. Now we will discuss Fourier transform and its applications in autonomous vehicles. Fourier transform is crucial for analyzing signals in the frequency domain, especially in radar systems. It helps decompose complex signals into their frequency components, which is essential for measuring velocity and detecting obstacles. Fourier transform identifies objects by distinguishing stationary and moving objects based on the Doppler shift in radar signals. The mathematical expression for Fourier transform is shown on the slide. Now, the first application is Doppler shift and radar signal processing. Radar in AVs measures the velocity of moving objects by detecting frequency changes caused by the Doppler effect. Doppler effect indicates that the reflected frequency is higher when the target is approaching, whereas a receding target will reflect a lower frequency wave. The Doppler shift is directly proportional to the velocity of the target vehicle. The transmitted radar signal has a known frequency, and when it reflects off a moving object, the frequency shifts. Fourier transform helps to compute this Doppler shift, and the formula for that is shown on the slide. This is an image depicting how the Doppler effect works. Next, fast Fourier transform. What is fast Fourier transform? It is a faster, optimized version of discrete Fourier transform, and it significantly reduces the number of calculations needed for signal processing, thus making our work much easier. Why is it important? In the context of autonomous vehicles, FFT allows the vehicle system to analyze signals from different sensors more effectively. It helps in separating different components of a signal, making it easier to identify important information like detecting obstacles or measuring speed of other vehicles. How does it relate to range and Doppler shifts? FFT is crucial for analyzing how the frequency of signals changes when the vehicle is moving. This can indicate how far away an object is and whether it's moving towards or away from the vehicle, which is the Doppler effect. This is an image depicting how fast Fourier transform works. The graph in the time domain essentially shows the signals received or reflected from various other objects. Using FFT, this is converted to a beat frequency spectrum, and the peaks in the beat frequency spectrum are nothing but objects at different distances. How does a radar work? Radar works by transmitting radio waves in pulses. Once those waves hit an object, they return to the sensor, providing data on the speed and location of the object. And like the vehicle's cameras, radar sensors typically surround the car at every angle to detect objects. Using MATLAB, I first constructed a signal with two frequency components plus some random noise, and then FFT was used to extract the frequency components of the signal buried in noise, which are about 45 Hz and 80 Hz as shown in the graph. The ability to isolate these important frequency components from the background noise is exactly what helps the vehicle detect obstacles, identify objects, and analyze environmental conditions. For instance, distinguishing sounds can alert the vehicle to nearby pedestrians or other vehicles, thereby improving the safety and response time of the vehicle. Some more applications of Fourier transform. Signal denoising and filtering. How does it work? The noisy signal obtained from sensors such as camera, radar, or LiDAR is transformed to the frequency domain first using Fourier transform. A low-pass filter is applied to remove noise and smoothen the sensor data. Then inverse Fourier transform is applied to convert the filtered signal back to the time domain. And the mathematical expression for inverse Fourier transform is also shown. This is a graph showing how filtering actually works. The first graph depicts noisy data in the time domain, indicated by the red graph. The next one shows the filtered data, indicated by the blue line, which shows the filtered signal. And the last graph denotes frequency domain representation before and after filtering. We can see a single peak in the blue line, thus indicating that a low-pass filter has been applied. The last application of Fourier transform that I will be discussing is image and video compression. Sampling and Fourier transform work together in video compression to efficiently reduce data size while preserving essential information. By managing the amount of data while maintaining quality, these techniques enhance the overall performance and functionality of AV systems. How does it work? Sampling first converts a continuous video signal into a discrete digital signal by taking snapshots of the video frames at specific intervals. Fourier transform then transforms the video frames from spatial domain to the frequency domain, helping to identify important frequency components. By sampling frames and applying Fourier transform, video compression algorithms can decrease the amount of data needed to store or transmit the video without significant loss in visual quality. Now we will discuss the impact and advantages of autonomous vehicles. First, improved safety. Autonomous vehicles reduce human errors, which are the cause of majority accidents. Using advanced sensors and signal processing techniques, autonomous vehicles can detect obstacles and thus react much faster than human beings. Second, reduce traffic congestion. Autonomous vehicles communicate with each other to maintain optimal speeds and reduce bottlenecks, thus leading to a smoother flow of traffic. Autonomous vehicles also use real-time data like traffic conditions and road closures and their stored maps to choose the fastest routes. Conclusion. In this presentation, we explored the real-world applications of convolution and Fourier transform in autonomous vehicles, illustrating how these concepts are not just theoretical but also pivotal in the practical applications of modern AV technology. We discussed essential classroom topics such as filtering, signal denoising, and image compression, along with some more advanced applications such as object detection using convolution and fast Fourier transform for detecting the Doppler shift of radar signals. Lastly, the presentation also highlights how these fundamental signal processing techniques also address critical real-world challenges such as traffic management and safety. Thank you so much for your time and attention.